For the introduction, this experiment focuses on determining the orifice discharge coefficient, which shows how actual fluid flow differs from ideal flow due to energy losses like friction and turbulence. The experiment used Bernoulli's equation to study flow through an orifice under both constant and varying head conditions. By doing this, we can improve our understanding of how fluid behaves in real systems. This experiment also develops our skill in setting up lab equipment, collecting and analyzing data, and applying theory to practical situations. It supports Sustainable Development Goal 9, Industry, Innovation and Infrastructure, and meets the requirements of the ECW437 standard. Next, problem statement. In many industries, such as water supply systems, wastewater treatment, and fluid transport, it is important to measure flow accurately to avoid design or operational problems. Orifices are commonly used for this purpose because they are simple and cost-effective. However, if the discharge coefficient is not correctly calculated, it can lead to wrong flow measurements. This may cause over-design, inefficiency, or even system failure. Through this experiment, we can study how different flow conditions affect the discharge coefficient, helping engineers design more accurate and efficient systems.
The objective of this experiment to identify the coefficient of discharge for a small orifice using flow under constant head and flow under varying head. Basic concept of this experiment is based on the basic principle of fluid mechanics, particularly how fluid behave when passing through a small opening known as an orifice. When water flows through an orifice, the change in diameter causes the velocity to increase, the pressure to drop. In general, smaller opening produce faster flow, while larger opening result in slower flow. The main goal of this experiment is to determine the orifice coefficient, which show how efficiently water flow through the orifice compared to ideal condition. To find the coefficient, the experiment measures the horizontal x and vertical y distance of the water jet as it exists to orifice. By using different orifice diameter, we can study how the size of opening affect the flow behavior and the orifice coefficient.
At first, we measure the height of water 45 cm using the ruler.
Next, place the orifice 4 mm diameter at the tips of reservoir and turn on the hydraulic bench, then adjust the water speed and the adjustable overflow until the water fills the reservoir with a height of 45 cm. When the water has reached a height of 45 cm, make sure the water is in a controlled state without waves and remains at the same height until the reading is complete.
To record the data, firstly we need to adjust the tip of the probes to be just in contact with the water jet. Next, record the tip of the probe profile on the graph paper.
Second condition, we measure the height of water 35 cm.
Next, lower the water speed and the adjustable overflow until the water fills the reservoir with a height of 35 cm. When the water has dropped to a height of 35 cm, make sure that the water is in a controlled state without waves and remains at the same height until the reading is finished.
Readjust the position of the probe according to the water flowing out.
A new reading for the height of the probe will obtain due to the changes of diameter of the orifice. Then, plot the height of the probe on the graph paper for all readings.
Third condition, we measure the height of water 25 cm using the same diameter of orifice 4 mm.
Next, lower the water speed and the adjustable overflow until the water fill the reservoir with a height 25 cm. When the water has dropped to a height 25 cm, make sure the water is in control state without wave and remain at the same height until the reading is finished.
Readjust the position of the probe according to the water flowing out. A new reading for the height of the probe will obtain due to the changes of diameter of the orifice. Then, plot the height of the probe on the graph paper for all readings.
I will now present the results obtained from this experiment. In this experiment, we conducted 3 trials. For all trials, we used an orifice diameter of 0.004 meters. The head levels for each trial were different: 0.45 meters for trial 1, 0.35 meters for trial 2, and 0.25 meters for trial 3. The volume used was 0.005 meters cubic. The time recorded for each trial was as follows: 16.21 seconds for trial 1, 24.23 seconds for trial 2, and 81.28 seconds for trial 3. To calculate the flow rate Q, we use the formula volume over time. Based on this calculation, the flow rates that we obtained were 3.085 times 0 power of negative 4 meter cube per second for trial 1, 2.064 times 10 power of negative 4 meter cube per second for trial 2, and lastly 6.152 times 10 the power of negative 5 meter cube per second for trial 3. This is the results that we obtained for 8 mm diameter of orifice. After that, for this experiment, we needed to determine the distance x and y from the graph. These distances were obtained from the graph plotted during the experiment, where x represents the horizontal distance and y represents the vertical distance. This is a simple calculation for trial 1 of the orifice coefficient experiment. In this calculation, we first determine the flow rate Q using the formula volume divided by time. The value obtained is 3.085 times 10 power of negative 4 meter cube per second. Secondly, we calculate the area of the orifice using the formula pi d squared over 4. The result is 1.256 times 10 power of negative 5 meter squared. Thirdly, we compute the coefficient of velocity Cv using the formula x over 2 square root yh, which gives a value of 0.825. Lastly, we calculate the coefficient of discharge CD using the formula Q over A square root 2GH. The value obtained is 8.266. Next, for this experiment, the graph showed that head level H with unit meter against flow rate Q with unit meter cube per second. So, y-axis is the head level H and x-axis is flow rate Q. For this experiment with 3 trials, the line graph illustrates higher head level readings with increasing flow rate.
The experiment investigated how water flows through orifices of different sizes under varying head levels. 2 orifices with the diameters of 0.008 meters and 0.004 meters were tested, and the volume of water discharged was measured for each trial. Results showed that increasing the head level led to greater flow rates, as predicted by Torricelli's law. The larger orifice consistently discharged more water due to its greater area. Differences between actual and theoretical values may be due to measurement errors, timing delays, or water splashing. In summary, the experiment confirmed the relationship between head height, orifice size, and flow rate, with results supporting theoretical predictions. In conclusion, the experiment successfully showed the difference between theoretical and actual fluid flow through an orifice. The discharge coefficient, CD, helps us understand the difference and is essential for designing efficient systems. The findings emphasized the importance of accounting for energy losses in fluid systems. Overall, the experiment helped us gain both theoretical and practical understanding of fluid flow and supports sustainable development, Goal 9, by promoting better engineering practices.